Hello all of you. In today's video we are going to start with language of chemistry. Language of chemistry is the first chapter in your textbook. We have finished this chapter in the class, but we are going to revise the portions which has been taught to you and also learn something new. Okay, now to begin with, in this chapter the first topic is symbols. Okay, now what is a symbol? Symbol is basically a short form of an element. Okay, when you represent any element by writing a short form, the shorthand form of writing the element is called the symbol. So a symbol has two kinds of meanings. When you look at a symbol, you can get two informations. One is you can either get a quantitative information or you can get a qualitative information. Quantitative information is that the symbol represents the weight of the element, meaning the particular symbol represents the atomic weight of that particular element. All right. The qualitative meaning suggests that the symbol represents one atom of a particular element. Is that clear? So quantitative meaning is that it represents the atomic weight of the element, and qualitative meaning is that it represents a single atom of that element. In the year 1807, the earliest symbol was given by John Dalton in the year 1807. He gave the figurative symbols of each and every elements. So back then, very few symbols and very few elements were known to us. So the symbols given by John Dalton was, he had given the symbol for oxygen, which was a circle, filled in circle, hydrogen with a circle and a dot at the center, and sulfur with a cross in the center. Eventually, in 1814, Berzelius gave the representation of a symbol which we still follow till date. Okay. Now, according to Berzelius's symbols, there were few rules set up. Firstly, the first rule was that the first letter of the name of the element is taken as its symbol. For example, the element carbon, the symbol for element carbon is capital C. The symbol for the element sulfur is capital S. The symbol for the element hydrogen is capital H. And the symbol for the element oxygen is capital O. The second rule was, if the first letter of the element's name is taken, then the first two letters are written together, with the first letter written in capital and the second letter written in small letters. For example, the element calcium has the symbol Ca. Silicon is written as capital S, small I. Since C and Ca are both taken, cobalt is written as Co. Selenium is written as Se. Since S is already taken by sulfur, we write Se for selenium. The third representation, or the third rule, was that back then the elements were known better by their Latin names. Okay, so sodium back then was known as natrium. Copper was back then known as cuprum. Its symbol was taken from the Latin name Cu, the first two letters of cuprum. Iron was Fe from the Latin word ferrum. And finally, gold, the Latin name for gold is aurum, and the symbol taken was Au. The second topic in this chapter is about valency. Valency is in short known as the combining capacity of an atom. Although this is the modern definition of valency, over the years valency has been defined in different ways. Especially it has been defined with respect to a particular element. For example, hydrogen atom. The number of hydrogen atom that can combine with any particular atom of an element or a radical or displace it, those many number of hydrogen atoms is defined as that particular element's valency. For example, let's take the example of hydrochloric acid, right? In hydrochloric acid, one atom of hydrogen combines with one atom of chlorine. So the number of hydrogen atom here is 1. So therefore valency of chlorine is also 1. Similarly, let's take another example, water. In water, 2 atoms of hydrogen combines with 1 atom of oxygen. Therefore valency of oxygen is equal to 2. In CH4, which is methane, valency of carbon is 4 because it combines with 4 hydrogen atoms. Now coming to valency of metals and nonmetals. Usually metals have a positive valency and nonmetals have a negative valency. This is because metals have a tendency to lose electrons and nonmetals have a tendency to gain electrons. Whenever an atom loses electron, it gains a positive charge. For example, potassium loses 1 electron to form K plus 1 ion. Okay. Here, since only 1 electron is lost, the valency of potassium is 1. So we are going to call potassium a monovalent element. Magnesium loses 2 electrons to form Mg plus 2 ion. And we are going to call magnesium a divalent metal. Okay, it is a divalent metal because it has a valency of 2. Similarly, aluminium loses 3 electrons to form Al3 plus ion. Aluminium metal is a trivalent metal. All of these are metals. Okay, potassium, magnesium, aluminium, all of these are metals. And if you look at the charges, all of them are positive. So metals usually form electropositive ions. Okay, so metals tend to develop a positive charge. So that nature of metals is called its electropositive nature. On the other hand, non-metals like chlorine, it gains an electron to form a negative ion. So chlorine gains 1 electron to form chloride ion. Oxygen gains 2 electrons to form oxide ion. Nitrogen gains 3 electrons to form nitride ion. And chloride ion has a -1 charge. It has a valency of 1, so it is monovalent. Oxygen, when it develops a charge, it has a charge of -2, so it is divalent. Nitride is a trivalent element. Okay, now all of these are non-metals. Non-metals which have developed a negative charge. Alright, so non-metals usually tend to form electronegative ions. This is the electronegative nature of non-metals. Now coming to the next topic, certain metals have a tendency to lose more than 1 electron. Okay, and form more than one kind of possible ions. So such elements are said to have variable valency. For example, I have taken copper. Copper exists in 2 states, Cu plus 1 and Cu plus 2. Okay, now to understand why does copper have variable valency, why does it lose more than 1 electron, right? We need to look at the atomic structure of copper. And if I want to draw the atomic structure of copper, I need to know its atomic number. So copper's atomic number is 29. If I need to write its electronic configuration, the distribution of electrons, I will write it as 2, 8, 18 and so how many are there? 18 plus 2, 28 plus 1 electron left. So that will be in the last shell. I see that there are 4 energy shells needed. So I am going to draw 4 energy shells around the nucleus. Okay. After drawing the 4 energy shells, I will fill in the electrons. So in the first shell, there are 2 electrons. In the second shell, there are 8 electrons. In the third shell, I will put 18 electrons. In the final shell, I will place only 1 electron. The first shell To recap, the first shell is known as the K shell, second shell is known as the L shell, third shell is known as the M shell, and the last shell in this case is the N shell. Okay. So after filling up all the electrons in the respective orbitals, now in order to show the formation of copper ion, Cu plus 1 ion, I am going to write down the symbol and the electronic configuration. The outermost shell consists of one electron. So that electron can be donated by copper ion to become stable, and it forms the Cu plus 1 ion in the process. Sometimes the second last shell, also known as the penultimate shell, okay, can transfer one electron from the second last shell, from its shell to the higher shell, that is the valence shell in this case. So when it transfers one electron, its electronic configuration becomes 2, 8, 17 and 2. In this case, the outermost shell contains 2 electrons, which is the furthest away from the nucleus, and therefore it becomes easier to remove those 2 electrons. On losing those two electrons, copper develops a +2 charge. Okay, so this is how copper develops a +1 charge and Cu +2 charge. Okay, now how do you name these copper ions? Because when copper forms its respective compounds, depending on what is the valency, the name of the compound would also be different. So if a compound has the Cu plus 1 ion, the Cu plus 1 ion in Latin, using the Latin name of copper, it will be named as cuprous ion, and the Cu plus 2 ion will be named cupric ion. So you notice that the lower valency of copper ion is named ending with OUS, and the copper ion having a higher valency is named with the ending the suffix cupric, IC, cupric ion on the as a suffix, as the superscript. The negative ion, example for a negative ion is carbonate ion. Carbonate ion contains 1 carbon atom and 3 oxygen atoms, together carrying a charge of -2. Okay, now radicals, positive or negative, can also show valency. Okay, so radicals also have monovalent, divalent, trivalent radicals. Ammonium ion here is a monovalent electropositive radical, and carbonate ion here is a divalent electronegative radical. Is that clear? Okay, now that we are learning a little bit about radicals, I think it's important to know the difference between ion and radical. Although we do tend to use the word ion interchangeably as radical, because we call ammonium as ammonium ion more commonly instead of ammonium radical, right? So to know the difference between ion and radical, ions are basically atoms of element, a single atom of element carrying a certain charge. It could be a positive charge or a negative charge. So when a single atom carries a certain charge, then that charged atom is called ion. Okay. Radical, like we defined a little earlier, when a group of atom carries a certain charge and shows valency, then those groups of atoms are called radicals. Some examples of ions would be chloride ion with a -1 charge. It's a monovalent ion. Okay, and then you could have chloride, bromide, fluoride, sodium. Okay, sodium ion is Na+1 ion. So all of these are examples of ions. Radicals examples could be chlorate, ClO3-1, or hypochlorite, ClO-1. With sulfur, you could form sulfite and sulfate. Sulfite is SO3 minus 2 and sulfate is SO4 to the having a charge of minus 2. Okay, so these are examples of radicals and ions. I hope the differentiation is clear between the two.